All right, let's do it.
All right, hello, can everyone hear me? Cool, I can hear my own reverb, so that kind of works out. Hello everyone, welcome again to this Streams meetup. It's probably the date you've been circling on your calendar for a long time, or maybe that's just me. Anyway, I'm Almog Gavra. I'm an engineer at the search infrastructure team at LinkedIn, and we provide a platform that allows the economic graph to be indexed so that everyone can retrieve the information that they need to retrieve, whether it's finding the jobs that they're looking for, or if it's recruiters finding candidates, so on and so forth. So, yep, that's me. Let's get right into the content. What is search at LinkedIn? How does it look like? If you guys aren't intimately familiar with the search sort of UI at LinkedIn, this is how it looks like. There's a search bar up top where you can search for be whatever you want it to be. Is it a person, a job? And it'll federate down to various different use cases from search. As you can see here on the top of the bar, there's a people search vertical, there's a jobs vertical, posts vertical, so on and so forth. Now, if you search without specifying a vertical, it'll federate down to all of the different verticals, and you can go from there and choose which one you want, whether, limiting it down or just want to see how it matches everything. In this specific case, we're searching for Jeff Weiner, the CEO of LinkedIn. Now, there might be multiple results that show up, so we also have to do some ranking to show up which documents come up first. Now, that's sort of the high-level overview. How does it work real quick? I'll give you a sort of an overview on search before I move on and explain how we use Kafka and Samza to update this economic graph real time. So this is the basic overview of our search infrastructure. We start out with a federator. The federator is what your query goes to at the very top level. When you send it to the UI, it goes through some UI things and then gets sent to the first layer, the backend in the federator. This does many things. The most important thing, in my opinion, for this presentation is that it updates the query that you send with information that might be useful for the future. So, for example, one of the things it might add is the connections that the user has. So if I'm searching for Jeff and I'm connected with Jeff, it might be good to know that as far as ranking. If I'm not connected with Jeff, but I'm connected with a different Jeff, my friend Jeff Schmo, that might also be useful. So I can rank that Jeff higher in the search results. That could be various things that the federator does. The second thing that it does is if you don't specify a vertical, like I showed in the previous page, it'll fan out to all of them. So it'll fan out to jobs, it'll fan out to people search, and all of the different verticals, and then mesh the results all together. That's the job of the federator. Next is a broker, which you can think of as kind of a mini federator, one for each of the verticals we have. Of course, they're replicated so that we can handle the amount of traffic that we need to handle. In this case, we can imagine we're sending it to the people search broker. It's a mini federator in the sense that it will rewrite the query from a generic query to something that's specific for the vertical that you're looking for. So in the case of Jeff Weiner, at this point, we know that Jeff is a first name and Weiner is a last name. So it might rewrite the query with that tag in mind. It might say, look for something with first name and last name to match your query. Whereas if you sent it to jobs, Jeff Weiner might be a company. So it would tag it as a company. That's unlikely in this case, but that would be the job of the broker, which then sends it out to the searchers. The searchers are what you can think of as the core of our retrieval. They are the ones that hold the index and actually have the data. So why are there three in this picture that are all colored blue? We partition our index. The index for people search is way too big to host on just a single box. So we partition it across many shards. The broker then fans out the query to all of the shards and combines them back together. Finally, sending it back up to the federator to do things like highlighting. So if you search for Jeff, the word Jeff will be highlighted in your results. So that's kind of the overview of the distributed part and the life of a query. What happens when it actually gets to a searcher index? When it gets to a searcher index, it might look something like this query, where you're looking for Jeff Weiner. But in the specific case, you don't know whether Jeff is spelled with a J or with a G-E-O-F-F. I know Jeff is spelled with a J, but this is for the sake of the example. Now, in this specific query, you can see pluses are required terms and questions are optional terms. So the first clause in brackets, Jeff or Jeff, means one of those must match, but the last name Weiner must match. So how does this look like when it actually gets to the index? It looks something like this. We have what's called an inverted index. In most databases that you're familiar with, you have a document ID that then maps to some forward index. So for example, document 1 maps to Jeff Weiner, LinkedIn, CEO, so on and so forth. In search, we have the opposite. We have the terms themselves mapping to the document IDs that have them. So in this case, documents 1, 3, and 6 contain the term Jeff, 2 and 7 contain the term Jeff spelled with a G, and 2 through 6 and 8 contain the Wiener. So how does a search actually happen? When we get this query, we look at all of them in order. We start at the earliest doc, and we match them all up. So we'd start with document 1. Since it matches Jeff but not Wiener, we continue to document 2. Document 2 matches because it has Jeff with a G and Wiener. So on and so forth for document 3. 5 doesn't match, 6 does. So at the end, we retrieve 3 documents, document 2, document 3, and document 6. Now, how do we know which of these documents are the best of them? For example, in this one, it could be that document 3 is the CEO of LinkedIn, the one that we happen to be looking for. This guy, he's document 3. But at LinkedIn, there might be many people that seem similar to Jeff Wiener, or maybe even impersonators of Jeff Wiener. In this specific example, we can assume we have 2 different Jeff Wieners that are not the real one, document 2 and document 6. How do we differentiate between these? How do we return the document that we actually want? Well, we use 3 different things. The first is query features. A query feature is a feature that cannot be stated independent of the query itself. So for example, if I have a query with many optional terms, so it's optional that he's CEO of LinkedIn, or it's optional that he lives in the Bay Area, those terms are, if those terms match in the document I'm looking for, it would be ranked higher. But since it's optional, it's only specific to the query that we send. The second type of feature is called the document feature. The document features are features that are specific to the forward index. So the document itself, Jeff Wiener, the CEO, might be ranked better because let's say it has more connections. Jeff is also an influencer. He's also often clicked on. All of these things would be sort of document features that, independent of the query, would make Jeff a better candidate result than the other 2. Lastly, we have a pluggable scoring model engine that allows us to have the same essential type of information and scoring model for all of our verticals. However, the verticals can write their own different scoring models. So articles, jobs, people search, they could all rank things differently while still using Galene, our search engine. Now, where does Samza, Kafka, all the streaming infrastructure play in? Well, it's really important to us to maintain strict SLAs. If someone updates their profile and changes their name from Jeff to Joe, we would want that to reflect pretty quickly because users immediately then search for themselves under their new name. It'd be a pretty bad experience if the old name showed up and the new name did not. So how do we handle this? There are 2 main concepts. One is the IO streams that you're all pretty familiar with if you're here. It's the Samza and Kafka streams. We also have some other streams at LinkedIn that I'll describe in a little bit. And the second thing is the concept of partial updates. Since the entire forward index of a document, so Jeff Wiener, CEO, LinkedIn, might not all live in the same database. Namely, at LinkedIn, we might hold something like connections at a different database than the user profile itself. So when a new person makes a new connection, we would get an event saying person A and person B just made a connection. We don't have the information of the rest of the profile. So it's very important to us to be able to add just this single term to the index and not the entire and not re-index the entire document. So that's something that Galene does on top of something like stock Lucene. So let's take a look at the life pattern, the life of a partial update. Here we're taking our favorite example, Jeff. Back in 2008, he was working at Yahoo. He was one of the executives there. Then he changed his company to LinkedIn. He updated his LinkedIn profile and LinkedIn showed up. How does this look like underneath in the search index? Well, let's assume we had Jeff, Yahoo, and Wharton. This is the document in a Lucene index that we have underneath the hood. What we do is we tombstone a field. We say the field Yahoo no longer exists in this document. So when you return this document, the term Yahoo will just not be in it. Now you're probably wondering, how do we know that it's LinkedIn? Well, we actually create a totally separate document in another index, which is a partial document. And this one has the same document ID as Jeff, but only one term. And the term is LinkedIn. And this mirrors the original document. So we would retrieve both, merge them into one coherent view, and then return that to the broker so that we have something that looked like just one document, even though underneath the hood it's 2. So that's how we do the partial updates. Now, how do we actually get these partial updates from the database itself? Well, at LinkedIn, we have many different types of databases. We have our classic Oracle SQL database. We have the open source Espresso key value store. We have Voldemort stores, and these all have updates that we need to capture. Now, When we capture these events, they get emitted to different systems. They might get emitted to Kafka. They might get emitted to Databus, which is an open source system that LinkedIn is also built to do exactly change capture. Now, at LinkedIn, we're currently developing something called Brooklyn, which is going to make these change capture events one cohesive unit of events. So no matter whether the underlying stream is Kafka or whether the underlying stream is Databus, we'll have sort of a guaranteed unified way to read from it. This Brooklyn stream has an underlying Kafka stream that we will then emit and read from Samza. What does the Samza application do? It takes the Databus change events and adds some information that may or may not be necessary for the search index, and it transforms the pure change event into something that's useful for search. So for example, if in the connections case where user A and B connected, then we would add an event where for document A, it's adding the connection B, and for document B, we would have the connection A. So in this case, one input event had two distinct output events that went to our index. So that all goes to search, we index it, and everyone's happy. But not that simple. There's obviously going to have some more issues here. Now, one of the issues we've noticed is schema evolution. How do we do this? So at LinkedIn, all of the events that get sent on the wire through Kafka are Avro events, which is simply a data serialization format. Now, the serialization of the format can change and evolve. For example, I might want to add a field. I might want to add title if the previous dot field only had first name, last name, and company. That all sounds good until we realize that there's a disconnect. Now the events in the stream that I've added might have it, but the events in the index, which I originally built it, don't. How do we resolve these two? At LinkedIn, we have something called a schema registry, where we register the schema with an ID. So every time we send an event on the wire, we'll actually prepend it with a ID, usually something like the hash of the index of the schema, when we can then retrieve that and use it as the writer schema. So that was the schema that was written. We'll take it and we'll read it into something that's compatible with our base index. Now, that's the schema evolution aspect of it, but how do we actually work with Samza? So the Samza application is sort of broken down into a few parts. One is the input event. We might need extra data to transform this event into something else. In this case, you can imagine that we need something like a text segmenter, which is, we use the Stanford text analyzing library to analyze any CJK languages and tokenize them so that we can actually index the events in some sort of coherent fashion to the index. So we might need various data like this. We might also need to make a RESTly call and get information that the original event doesn't have. So for example, if we know that person A changed his title to senior software engineer, we might have a standardized entity version of that. That might be an ID 7, title ID 7. So we could fetch that from an external source that didn't have in the original event. This all happens in our Samza job. Then it's transformed in a very generic way that each of our verticals can write their own transformers and plug them in pretty easily. In fact, we had a very explicit goal with this project to be able to have verticals configure all of the Samza application in about 20 lines of code. Now, the transformers are not included in this, but plugging them in is super simple. I can talk about this a little bit more in the discussions at the end if anyone's interested. Now, we ran into a few more issues. One of them is that we noticed that some events were more important than other events. In this example here, you can imagine that we're consuming from 3 different streams. The first stream could be a connection stream, the second could be a profile update stream, and the last could be a location update stream. Some of these streams are just more important. So for example, we might not need to index immediately the fact that you connected with some other member. However, if you changed your name, it might be pretty important that we get that immediately. So how did we solve this? Well, we rate limited streams that aren't as important. So the connection stream might have very high throughput, but if it's going to be overshadowing the events that are more important, we simply rate limit and output it into the transform metric. So in this case, you can imagine that we would take the second event and actually put it through. We did this through the Samza message chooser, which is an interface that Samza gives to you. This is particularly useful because the message chooser will only choose an event from a system after you've output an event from a system. So we didn't need to do any buffering for our rate limits. And in fact, we only requested the events when we needed it, which was a pretty big win as far as sort of GC and memory constraints go. So that was the first thing we noticed was really helpful. The second thing we did is some performance tuning. I'll get into the exact scale of our job soon, but the scale was really high and we couldn't process all the events and the number of containers we needed. So how did we handle this? One thing that you guys might be familiar with is Samza has a grouper where you can group certain system stream partitions into different tasks. Now, the tasks can be run in parallel. One of the issues we noticed, however, with the default system stream grouper is that a lot of our sources only had one partition. And everything that had one partition was being moved and grouped into the same task. To handle this, we noticed that there was a system stream partition grouper. So what does that do? It means it groups by system stream partition and not just system stream. So the streams that had only one partition would go to different containers. In this diagram above, you can imagine the connections in the location stream only had one partition, but they were actually moved into two different Samza tasks. So that helped us get some speed up, but that wasn't quite enough because these single partition tasks had so much QPS, we needed to actually get one step further. How did we do this? Well, we had something called parallelism within the task. This is, for you guys who are interested, the task.max concurrency setting in Samza, but there was one issue with it. We were able to get 1000 QPS, which is way more than we needed, but it had events out of order because you don't guarantee the ordering when you have the parallelism. So we're currently working on handling this in various different ways. The first, we're thinking of just moving these streams, which are single partitions, to a Brooklyn partition source. This is going to happen later this quarter, and we're going to have happy events. But if that doesn't work out, we can always implement a message collector and always reorganize the tasks, the out-of-order events as they come in. So I've been talking about this as if it's the greatest thing ever. What scale does it actually scale to? So here's some numbers. And this is all in one data center. So of course it scales horizontally across data centers as we want if we need to increase the traffic to a specific data center or spin up a new one. Now in each data center, we're getting about 10,000 events per second. That's about 14 million updates daily. The bulk of those are from people and articles. It turns out there's a lot of people updating their profiles and a lot of articles being updated at the same time. So that's just to give you a rough estimate of the scale. The next thing is, how did we get to this level of scale? Well, there's three things that were really pivotal to achieving it. The first part was using Yarn in Samza. If we get more live updates, we can, as we want, on demand, scale that up. That's really nice because we have something like 256 partitions for most of our streams, so we could scale it up from the usual number of containers to essentially as many as we could possibly need. If you're at the streams meetup, you probably know that Kafka is a pretty scalable solution, so we've been using that across all of our data systems, and they're working really well. And lastly is the index partitioning that I mentioned at the very start. If we ever need to index events faster and we can't hold it in the number of partitions we have, we can repartition our index, have them in more partitions, and send them into sort of smaller chunks to each index. That's the current state of things. What are some issues that we have with our live update system that we haven't been able to address at the moment? One of the really important things that we have in search at LinkedIn is static rank. Since we have so many documents, and a query like Jeff might match thousands, if not millions of documents, we want to be able to only score a subset of them. So we order the documents based on document features when we build the index. In this case, we also assign it a document ID that's lower. So if you remember the first slide where I talked about the inverted index, we scan the index in order of document ID. So we'll see the lower documents before we see the higher documents. In this case, you can imagine the query is to retrieve Jeff, but we only need to retrieve 2 Jeffs. That's enough for fulfilling the intent of the query. So we would retrieve the first Jeff, we would retrieve the second Jeff, and this would be the result set. We wouldn't even look at the third Jeff, even though it met. So why does this pose an issue for our live updates? Let's assume a new document comes along. We only have in sort of abstract this one document. We don't have it in relative form to the rest of the documents. So what do? We either give it a document ID that's greater than all of the other documents or worse than all of the other documents. So when would we use either one of those? For people, for example, you can imagine that new users are probably less likely to be searched because they have fewer connections, they're not influencers, they don't have a very up-to-date profile, so on and so forth. But jobs, a new job that comes, is probably one that's very attractive. It's one you haven't seen before, and a new job opening is usually a good one. So those are the two different uses, but we could get better. How does it work in the offline flow? You can imagine we have this entire set. So every once in a while, we build our index offline on Hadoop and have a view of all of the documents at once. We'll take these documents and we'll put them in order as is. So here in this case, the Jeff with a question mark would be third. So it's better than Jeff 6, but worse than Jeff 2nd. This type of update pattern is really difficult to achieve with live updates when we don't have a full view of the index. So that's currently the issues that we have with some live updates. Other than that, it's been working pretty well in production. You can update your profile and see it in search pretty quickly afterwards. That's that. If you guys thought this was really interesting, Search Infra is hiring, and you know, this can be your everyday. So if anyone has questions, I can now, I think I have like a few more minutes for questions. So yeah. Yeah. How do you decide rank in static rank in people search? So I actually don't work on the relevance side. I don't know exactly, but when we build the index on Hadoop, they have a very specific model that they use and they apply to documents. Since you have the view of all the documents in your shard at once, you can apply them to all. Now it's not global, it's per shard, but that doesn't matter because the searchers are only per shard. So as long as it's sort of relevant per shard, that's enough. It could be something different, yeah. Shy crowd. All right, cool. So I guess we can pass it on to the next speaker.
Right. So